For those of you who do not know me, my name is Ali Kujuri, and I'm an adjunct professor at the Engineering Science Department and one of the organizers of this lecture series. Mr. Sharon Marivani and also Ms. Kate Lapp also are the other organizers for this series. On behalf of the School of Science and Technology and of course the Engineering Science Department, I would like to thank you all for attending this 8th lecture in this academic year and 131st lecture in the series since we started in 2006. Before I present our guest speaker for today, let me mention that we have ordered pizza. In fact, Kate has ordered pizza. It's delicious, by the way. And we hope that you stay. I mean, it's going to be here at 5:30, and you'll be here at that time, and then you can enjoy having the pizza. Our guest speaker for next time, on March the 1st, that is Dr. Sudhir Shrestha. He's an assistant professor, Engineering Science Department here, and the title of his talk is Smart Sensing Systems and Analysis of Exhaled Breath for Detecting Diseases. Our guest speaker for today is Mr. Peter Carlson, and the title of his talk is How Technology Helps Save the World's Most Valuable Resource. Mr. Carl Peterson is a co-founder of Hedgehog Data Systems in Petaluma, California. He has 15 years of experience using distributed data systems and scalable software as a service solutions to build IT products and services for enterprises ranging from small to Fortune 500. Previously, Peter was Vice President of Engineering at Shaman Corporation, providing industry-leading award-winning IT data services. Prior to Shaman, Peter held environmental management positions at UC Berkeley. Together with Chris Spain, the HydroPoint CEO, Peter holds a patent on controlling a resource demand system. He is an assistant scout master for the Boy Scouts and splits his remaining spare time between snow camping in Yosemite Park, National Park, and scuba diving in the Caribbean. So here he is.
Thanks everybody for coming. We'll bring up the presentation in a second. As Ali talked about, we're going to be talking today about how technology can save the world's most valuable resource, water. And just to kind of give some context to this, water is a very precious resource and we're running out of potable water. So it's predicted that within our lifetime, a city populated with millions of people will run out of water. That is called day zero. Unfortunately, day zero is coming sooner than we think. So May 11th, 2018, Cape Town, South Africa is on track to hit day zero. So what does that mean? So right now, they are on rations. Everybody's got rations, but the taps still work. On May 11th, unless they get additional rain or other sources, those taps will be turned off. Those people who live in Cape Town will then have to walk to a government-sanctioned spigot to get their controlled allocation of water in order for them just to live, right? So water, we can only go 3 days without water, and getting that water is critical. So day zero is upon us sooner than we think. The question is, will we respond differently when day zero hits us? So right, this is an example of the Bellagio in Las Vegas, and as we approach potentially some areas of day zero in the United States, how will that affect us? The question is, where is that happening? Miami, Florida is currently on number 11, but still in the top 11 cities right now, scheduled to hit day zero within a decade. So the question is, why? Water is ineffectively managed, it's wasted and lost. Nobody's really tracking that water usage. It's really difficult to transport, and you have to transport it from one location to where the people are. So right, you have to transport it to the right place at the right time. And then finally, it's all distributed, all these different water. There's over 4,000 water agencies in the United States, and they all have different availability, and the cost varies across all of these different areas. Water waste is everywhere. 40 out of the 50 water managers across the United States have said that under average conditions, they will run into water shortages sometime within the next decade. Irrigation is one of the largest water uses for urban area in the United States. Let's just go through an example. So here we have irrigation, and you can see that it's kind of running off here into the stream, but that water actually goes down into a sewer drain. That sewer then goes potentially onto a beach. And in this case, we had an area in Southern California to where they were fertilizing their landscape. That fertilized landscape, when they were having runoff, would go in through the drain. That would go all the way down to a beach. And due to the extra bacteria that would be created when that fertilized water would go onto the beach, it would actually cause beach closures. So this is just one example of where inefficient water use, water waste, is essentially having additional impacts beyond just lack of water. Another example is you walk into a yogurt shop and you go, what does this have to do with water? You get some yogurt, you get your favorite flavor, you walk in, you walk out. But if you look behind the scenes, all of these machines are being cooled by water. So we had a large mall. That large mall had a yogurt shop, which was essentially using 600 gallons an hour of water, about 400,000 gallons a month, where that water was just being literally, as you can see, flushed down the drain. The mall was paying for all of that water because it wasn't a restaurant. They didn't sub-meter the site. They didn't go and say, you're a heavy water user. It was a yogurt shop. But once they found out, with some of our technology, that they were having this waste, they were able to go find out that it was this yogurt shop, and the cost of the yogurt shop over $3,000 additional per month to go and be using water as a cooling agent for their yogurt shop. And the risks are more than just costs. So poor plant health, moldy foundations, hardscape damage, slip and fall injuries, as well as pollution runoff. Combined with all that, water is the fastest rising utility cost in the United States, faster than inflation and faster than all of the other utilities combined. So and this is from the Bureau of Labor Statistics. So as we go and see, water, typically people think, turn on the tap, get some water, it's very inexpensive. The cost of water, what's going up, but what's a benefit of that is now it's being worth managing. Now people will start to pay attention. So water waste is no longer economically, legally, or socially sustainable. That's our premise. And how do we solve this problem? Well, HydroPoint, my company, believes that we're going to solve this problem with data. By giving people data, by managing with data, by using information systems, whether they're IoT systems or control systems or visibility systems like billboards, by giving people and devices data, we'll be able to better manage this data, control it, and hopefully we won't ever hit day zero. So we're going to start collecting the data, analyzing the data, providing the data through information systems like websites or user interfaces, ultimately so that people can take action. We believe that big data needs to meet big water. And HydroPoint, overall, we can go on to the next slide. There we go. Is going to use this data to transform water use globally. So how are we going to do it? Well, we believe that we're going to start using, at the very basic, by using data acquisition and control systems. So it's not just using flow sensors. We're actually going to be using weather data, water use data, site and alert data, user data, as well as have devices in the field that can provide some control. All that information and data connectivity essentially goes into our analytics engine, which crunches all of this data, makes sense of it, and then ultimately provides applications to users. WeatherTrack does this by having, the slides got slightly rearranged. WeatherTrack does this by three main offerings. We have WeatherTrack, which is our irrigation system. We have Water Compass, which is our real-time leak and flow monitoring. And we have HydroPoint Performance Management, which is associated with professional services to ensure that those products are successful. Let's understand how WeatherTrack works. So the first part of an irrigation control system is not thinking about the water, it's actually thinking about the data. So we're collecting over 8 million data points every day so that we can convert that data into relevant site-specific weather data. Because in order to manage the devices in the field, we need a smart scheduling engine, not just somebody to kind of guess at how much time to run on a device. We need something that really is connected to what the plants need, which is the plants need water based on what the weather was. And so we go and create a scheduling engine which calculates irrigation schedules based on the weather. And that's where the WeatherTrack name comes from. So that's what we did initially. That was back in 2002, we did that over the paging network. And then we realized that we were really missing out. We're missing out because we're missing the other side. What happens when an event occurs? What happens when you've got flow going and nobody knows about it? You've got a leak, but nobody knows about it. And so now we've got two-way systems over typically a cellular network. That data goes back up through the cloud, right, when that alert occurs, and then gives access and notification to users either via a website or via their mobile app. All of these pieces kind of come together in a set of components. One of those is our hardware components. We've got irrigation control devices, flow control devices, flow sensing devices, mobile apps, and web apps. So all of these pieces, here's of all the different, I've looked at your different hardware projects out there. We take some of that information, right, and we create our own hardware components ultimately to provide both sensing and control capabilities. We then, in order to get that site-specific weather data, we go and calculate site-specific high-resolution weather data. We first collect over 8 million data points, including topography, vertical pressure profiles, half-kilometer level, topography data where we're going and looking at the soil types. All of this information then goes into a physics weather-based model. So we go and take a bunch of raw data and put it into a fancy weather model that actually goes and calculates based on climate physics what the weather's going to be for every square kilometer. We're doing all that in the cloud that ultimately provides ultimately provides the ability for us to go and track weather at a very detailed level. So as you can see on the left, where you might have a dry part of the city or an area, all the way through to where you have a lush side, you have variations in temperature and wind, and overall there's a factor that we call evapotranspiration, which is the amount of water transpired from the plant leaf as well as evaporated from the soil. We're able to go and calculate that information across all of these different various weather types. ultimately go and calculate and model down to about 1 square kilometer. We had a study done on us by a group in Florida, and that study showed that we were within 2% of a weather station that we knew nothing about. So that weather station was done by a research organization, university, and they were wondering how good was our weather data. So they put up a weather station miles away from others, and then compared our weather data to that location that we went and calculated. So weather data is an important part, but now I've got weather data. What other information do I need? Well, one, we need plant type. Some plants need more water than other plants. We need root depth. How much water do we need to put down, because the plants can only uptake water to where their roots are. We need to know how much water that soil holds. So clay soil, right, can hold a reasonable amount of water. Sandy soil can't hold much water at all, right? You go to the beach, pour water onto the sand, doesn't hold much water at all, where clay soil can hold a lot of water. You get into the climate, the microclimate. Is it sunny or is it shady? And ultimately, you get into slope. Do we do lots of little squirts of irrigation, or can we just put it on a flat surface and just irrigate all at one time? And finally, the sprinkler type. The sprinkler type says how much water is coming out, how much water are we putting on that landscape all at one time. And then with these different factors, we go and calculate a schedule. So just going and providing a reference, irrigation schedules used to be like thermostats. You go and set it, and whatever you told it to set it to, that's what it did. Maybe you set it once or twice a year. You don't really change it that often. Irrigation controllers were the same. In traditional timers, they were called, whether it rained, it was foggy, it was windy, it was sunny, it was always running the same schedule. With weather-based irrigation and smart timers and smart controllers, we're able to figure out, based on each individual area, how much water that individual plant needs and what the weather is to go and figure out when it needs that water. So again, with all these different factors associated with the landscape and the weather data, we're able to go and incorporate this smart scheduling engine to get the right amount of water down at the right time. A new area that we've also been focusing on is, great, you guys have figured out how to better put down the water onto the landscape, but can you do it for every spot? What comes out that city parks, for example, or areas that are frequented by the public only have very limited water windows. They can only put water down in a very short amount of time. Well, that can be very difficult, and so with these different systems, and so they typically are running these long water windows, and it takes a lot of human management to do that, because they have to start to think about water windows, site usage patterns, pipe sizes, pipe materials, pipe schematics, hydraulic capacity, and the list goes on and on of the different types of things that they have to think about in order to get that water optimized. And by using data, by using this information that we're able to capture through sensors, we're able to optimize. I forgot to mention it, but here on the initial one, the duration of the time was 16 hours. So in an unoptimized schedule, it was 16 hours. When we're able to take all those elements into account, and we're able to optimize that schedule for that site's needs, we're able to knock off 10 hours over half the time and get it to run in about 6.5 hours. So that's WeatherTrack. WeatherTrack, again, is about smart irrigation, about putting the right amount of water down at the right time and getting that right information to the right person at the right time. Then, as we had our customers start to say, you guys are doing a good job, what about if we look indoor? So as we were outdoor with WeatherTrack, they then said, we think we have water problems. We want to get information about our leaks that are inside. So we created Water Compass. One of the areas that we saw was that even small leaks can add up to a lot of water as well as a lot of dollars. So if you have a leaking toilet, which is probably the most common leak out there, over a day, it's 720 gallons. Sometimes, right, maybe people have done it here, go, oh, my toilet's leaking, I'll fix it in another day, right? For every day, that's 720 gallons. If that goes a whole month, that's 21,000 gallons. And ultimately, if you let it keep going, and it doesn't annoy you, it's 262,000 gallons for a year. And that's just a toilet leak. So Water Compass was designed to get real-time leak detection and ultimately escalation, because it's not if you're going to have a leak, it's when. In fact, on 99% of every Water Compass device that we've installed so far, we found a leak. That's a scary statistic as far as how many leaks are out there on these different sites. And we're able to do great real-time analytics, provide people usage and visibility patterns, and bring all this data together through a user interface that allows people to take, again, actions. How does it work? We have a device that we call a flow monitor, and you first install it on your existing water meter. You don't need to cut into a pipe. You just go onto where the water agency currently bills your water from, and you install a Water Compass flow monitor. We then calibrate it to that individual meter. We then start, it's using cellular connection. We then start collecting that data. That data normally goes up on a daily basis up to our server and gets analyzed. However, we're able to put thresholds in and to be able to put it up more often if we see super high usage. We then upload that data, and ultimately, we alert the user if they have any hidden leaks, large or small. Here are some installation examples. Some of them include regular water meters, like down here. That can be a dedicated irrigation meter. It could be a meter that's going into your house. It could be a meter that's going into a property. And there are different sizes and shapes and types of meters. There's also one of the other bigger water users out there is called a cooling tower. A cooling tower is designed for cooling down large systems where there are compressors, essentially. Compressors get very hot and they need a way to cool down. And so water comes in, gets this heat exchanger over here on the right-hand side. Water comes into that that water cools that heat exchanger, and as it comes, that warm water comes up to the top, it gets sprayed, and the water essentially evaporates, comes down, and gets recirculated. Some of that water gets evaporated because it's hot. Some of it gets drift because there's wind going by the top. Ultimately, you have to fill up with makeup water to keep putting the water into that system. And then because you have salts and other components, sometimes you need to what's called blow down or get rid of some of that water in that blow down. That whole process, people don't really regulate. It's a self-regulating system, but the problem is it doesn't regulate well all the time. So if suddenly water is starting to spill over because the makeup water is left open, nobody really sees that. And so with our system, with Water Compass, we're able to get real-time visibility on these types of systems to be able to provide alerting, alarming, and overall usage patterns to help them run these water cooling towers more efficiently, as well as let them know if they have any anomalies. Now, we haven't done it yet, but one of the areas that we're talking about, right, is we have this great weather data. The cooling tower should be correlated, the cooling tower use should be correlated with that weather data so that we can utilize, again, more data to get more answers and help them solve these problems. Finally, all these systems, unfortunately the area that we're in doesn't have a lot of people who have a lot of education. Landscapers on the irrigation side typically know about plants and plant types. They're not really water people, they're not irrigation people, they're not hydraulic people, they're not engineers. And so one of the things as we think about all the data that we're throwing at these people, here's this list of data that we've got at the bottom. It's a lot of information. The question is, how do we provide that information in a way that people can understand? So we've developed a professional services group which essentially helps people, help customers take all of this data and roll it up. So from all this, people can usually understand about 3 things, right, when they keep in their mind. We were able to roll it up into 6. And we said, well, that's not good enough. 6 is too many. So finally, we were able to roll it up into 3 main categories and provide the overall service: savings, risk, and operations. It makes sense to an end user. It makes sense to somebody, a property manager who cares about money and who cares about how the property goes. So we're able to provide it in 3 main categories, and we give people grades and site grades, and it's really working out well. People really, it makes sense, and we're taking, again, all this complex data and rolling it up into simple factors. Some of those examples include, here's a report card, simple A's, B's, associated with those, graphs and charts. We're able to also show them what was their usage before and what was their usage after. So we have a baseline usage before, and we have a target of where they want to be, and then we can compare ourselves to how well we thought we were going to do versus how well we're doing. Ultimately, HydroPoint believes that we will solve these problems by getting even more data. We currently have about 226 gigabytes of data in our current database of just operations, and about 235 terabytes of data. Again, that's 235,000 gigabytes of data in our high-resolution weather data. And that's just us getting started. So now we're going to start collecting more user data, more sensor data, as we get more devices out there in more locations. All of that information, again, will be brought together to help us provide more use and more data. So going forward, as I just said, we're going to continue to collect more data. We're going to then start using even more analytics beyond what we've done today. We never talked about machine learning of what we're doing today. That's a future project of where we're going. But now that we've got all this data, we can now start using even smarter algorithms to go forward tomorrow, ultimately providing, again, great interfaces for the people who have to take the actions. Because if we're just providing them data, it's typically overwhelming. You have to provide actionable data, data that these people can understand and that they know explicitly what to do and how to resolve their problem. Whoa. I think I'm missing a slide, but ultimately, it's expensive to deliver water, and unfortunately, and it's criminal to waste it. So that's where HydroPoint is going to be providing data, essentially, to be making actionable data and reduce waste with water. Thank you. Yes, sir.
Yeah. Do you provide the service, your service, to the public or just the companies and so forth, or both?
So we provide our service to typically business-to-business customers. So because we provide additional services and additional analytics, it makes sense for businesses to buy that versus residential. We initially started on the residential side, but quickly realized that the businesses were the ones who were much more interested in it.
Yeah, the reason that I'm asking that is that when you take a city like Los Angeles, which has like maybe several millions of
too many people,
households or whatever.
Yep.
Now, putting all of these, shall we say, sensors, in a house, inside and outside. I mean, there are tens of sensors that you need. For example, for inside, you are going to have the washer, the shower, all of the faucets, the toilet, and all of that. I mean, there are many of them. I mean, and the refrigerator. And then when you go to outside again, the same thing. This is going to be very much. I mean, it's going to be a big thing, and I'm talking about the scalability of this. I mean, what?
Yeah, there's some other companies. Phyn is an example, PHYN, right. And what they've done is they actually have they put a device typically underneath your kitchen sink, And then they have a pressure sensor. And they actually look for the water hammer, so that when you turn on your faucet within upstairs, or you flush your downstairs toilet, even though they've got one pressure sensor within their house, based on their machine learning algorithms and their sensitive pressure sensor, they're able to not only determine that you flushed a toilet, they're able to determine which toilet that you flushed and how much water was used. So there's definitely systems, right? And looking at how many sensors do I need, some people are reducing the number of sensors they need, right? And others are saying, hey, we need to be able to submeter where all that water's going.
Yeah, so what I'm talking about is just the scale of this thing. For example, when you take PG&E or let's say the water company, they just bring the water or electricity to your house, and then you just
Everybody needs water.
And then whereas when it comes to your thing, your data collection and so on, it really is a big thing as far as all of the installation of the sensors, and then getting the data, how to provide energy to these sensors and so forth. I mean, and so that's what bothers me to understand. I mean, how big this whole thing is.
Yeah, it's it's definitely pretty huge, right, from that perspective. And it even gets strange, right? So in electricity, you can have a device that kind of maybe takes some of that electricity to power itself, right? In water, you typically don't have that, and so you need to have it be battery powered. You need to learn how to use and do that sensor collection with, intelligently using those batteries, right? And over long periods of time, 5 or 10 years, to be able to do that. And we're doing that today. Our water compass device lasts around 5 years in the field while still collecting all of that data and providing a daily upload.
All right, thank you.
Yeah. Any other questions?
Do you measure soil moisture, and if so, what sensors do you use?
We currently, HydroPoint acquired another company called Baseline out of Boise, Idaho. They actually have their own soil moisture sensor using a patented way in which they go and put a circuit board essentially with a path where they go and look at the time that it goes and takes to run a signal over that particular path. And they use soil moisture sensors to go and accomplish a similar system, but with soil moisture sensors. So instead of weather data, soil moistures.
So is your company affiliated with agriculture? Because I know they use a lot of water and there's a lot of potential waste, so do you monitor that at all?
We don't currently link in with agriculture yet. We're looking at that. We've done some studies with fixed crop areas, but we currently don't do anything in agriculture. But you're definitely right, agriculture does use a lot of water. Anybody else have any questions?
How much is the water company, you kind of mentioned you're staying away from like the residential areas. How much does the water company usually run?
How much does the water compass usually run?
How much for like a business or like, because you said they just need one water compass, right?
Yeah, so it typically per meter, but a typical water compass runs, it's essentially about $600 a year is the ongoing fee associated with water compass. So that's why it's not necessarily geared toward a residential customer. It's about $600 a year for the ongoing service of that for the business.
Yeah, I have a couple questions. One is, I have a lot of interest in transducers and sensors. What is the state of the art in terms of accuracy for water flow meters?
So on the water flow meter side, we don't do that directly, but we do partner with some people. And right now, there's kind of two main. One is an ultrasonic flow sensor, and I don't really, so for example, if you had a 6-inch water pipe, right, it can read down to about 2 gallons a minute.
Okay.
So I don't know what that translates into feet per second, right, but a fairly low amount of water, sub-gallon per minute on less than a 6-inch pipe.
So the accuracy, in other words, you take that data and you're making decisions based upon
Yes.
the data. What do you assign as for the accuracy of that?
So again, it depends upon the individual flow sensor, and
Right.
so how do we use the accuracy, right? Essentially, we have an error bar,
Okay.
right, around what we are measuring.
Mm-hmm.
And that error bar, right, if it's an inaccurate sensor, right, has to unfortunately be bigger, right, because the error could be bigger. And a more accurate sensor, like an ultrasonic or a mag meter or something like that, the error bar can be lower, right, to provide us more consistency. The other scenario is, as we talked about, pressure. Pressure is an important element, and as the water agency provides different pressures to different sites, the actual flow rate based on the hydraulics and the pipes and the regulation, because there's typically not flow regulation on those sites, can actually vary also. So there's two elements. One is the accuracy of the actual flow sensor, and then what is the consistency of the pressure being provided by the site.
Okay, the second question I have is, I manage a group of houses out in West Sonoma County. We have one well and multiple houses, and the issue that always keeps coming up is who's using more than their fair share of water?
Yeah.
Okay.
These
So,
small water agencies, yes.
Your talk catches my interest because this is the kind of thing we would really could find valuable in monitoring the water of each of the houses.
Yeah, so there's, we definitely have had some small water agencies, right, or even now some bigger ones, look at basically providing our device, right, onto those for doing monitoring of, you know, basically either real time or even monthly roll up to provide bills. That's not something that we were initially focused on, but now that we're starting to see some customers see that, it's an area that we're looking at.
Okay. Yeah, that's definitely an area of interest to me. And then my final question is, when is day zero for this area?
There's currently no scheduled day zero, hopefully far away from now, but as I said, you know, even in the United States, Miami, right, because of salt intrusion is the reason why, right, they're actually getting closer within a decade is kind of the current date. Any other questions?
So I was just wondering, in terms of sensors, have you got a sensor that you think if it reached a low enough cost point, it would be valuable to inform the process of saving water? So I mean, like, I think you did mention capacitive, the water sensors on the ground, but are there any other sensors?
Yeah, so the sensors that I had talked about from a company that Finn, right, for those to be able to be hooked up, it's one sensor that can read a whole area, right, versus having lots of different sensors. I think as that price goes down, that can really provide some great insight into valuable insight. The other one is pressure sensor. So as we talked about, right, the variability of a flow sensor has a certain accuracy to it, but then you have this pressure variation, and if we're able to better understand the pressure variation and the flow sensor accuracy together, right, then we'll be able to go and even make that tolerance associated with how much water we need even lower to basically minimize any waste.
You mentioned that you also develop your own hardware. Obviously, there's a lot of data analysis. And I was wondering, what kind of equipment do you usually look for people who work at the point in terms of?
Yeah, great question. So, so we've got, so we decided to make it hard on ourselves. Because we started back in 2002 and then went into the commercial space in 2007, there weren't a lot of the Andrino or other kind of IoT systems that are today. So we developed all of these systems essentially from scratch. We developed the actual PCBs that are within our devices. We developed all the firmware that are within those devices. We developed the communication between our devices and the cloud, right, over a cellular network. So we went with low bandwidth because at that time cellular bandwidth was very expensive. We then developed all the protocols and analytics on top of that, and ultimately the web interface. So we decided to do full stack, and we mean full IoT stack, from device all the way up into the cloud. So on the hardware side, we've got our devices, our controllers. It's interesting, a lot of people today tend to know a lot about digital circuits and how to make digital circuits. One of the areas that we're seeing is, because we're in the field, because we're managing solenoids, because we're managing kind of these real world things versus just computers, having some knowledge of analog circuits and understanding how analog circuits are fitting into power requirements and power boards is one area that we're have been using and found use there. Also on the display part, right, when we have our digital display, being able to understand where all the pixels are and go and use libraries to go and create a good vivacious user interface. So there's devices, again, we're connecting up to devices in the field. We have to account for things like surge protection from lightning. And so all of those elements kind of fit together into ultimately our devices that are in the field. I don't know if that answered your question enough. Specifically, we use, and Brian would know this better, specifically we use a PIC 32, right, for all of our processing to go and capture all of that information. And then ultimately, we have a cellular device which then we're communicating all that information out. Did that answer your question? Oh. Yeah.
What kind of cloud services do you use? Or like what infrastructure do you use?
So initially we kind of did it all ourselves. We're in the process right now in the next 2 months of really moving over to Amazon Web Services, which I think I've seen on some of your different posters. So what's really great about Amazon is they're able to provide all of these different tools, and by moving there, we're able to take advantage of a lot of these different tools versus having to kind of continually develop it ourselves. We're able to now start to use their tools, and things like machine learning will become much easier.
That's a question for our senior students. Basically, what areas and sort of what skills do you expect or do you need for your company?
Yeah, so we need so many. I think the areas right now of growth, right, are in some ways in our analytics. So we're starting to capture all of this information and looking at that information and figuring out what better information, what better insights can we get from this information. So being able to understand data, being able to use programs like R or other analytic engines to be able to do that, which ultimately, right, would be put back into a highly scalable system, right? But that's one element. I'm trying to think about on the hardware side, do we have any, Brian? Brian's our HydroPoint's VP of Engineering, so he would potentially have.
Yeah, I mean, you know, one of the things is definitely as the communications network changes, we were constantly looking at changes there. We're right now evaluating, you know, LTE's been out for a while. The M class, which is really geared more towards IoT, those, we're just prototyping some of those parts right now. So we're taking a look at that and deploying it, and actually running into a little bit of trouble. I was just reading before I came over here. But yeah, so that, you know, as a communications network, that's something that we're always working on. Cost is always an issue. We're always looking at trying to reduce cost of boards and that, of the controllers that we have out in the field. So, yeah, I guess Peter just kind of...
And even linking in other, right, we talked about earlier, linking in other types of devices, other sensors, right? How do we become part of a bigger network, right? Is that over radios? Is that over physically wired?
Right.
As we
Pressure sensors
pressure sensors. Our goal again is to collect as much data, because with that data we can make smarter decisions.
Actually, talking about sensors, there is kind of a little bit of a debate. I don't know, Peter, there's kind of weather-based sensing, and then there's the, you know, in-the-ground sensing. There's a little bit of a philosophical part to that. So both of them have got pros and cons. You know, the sensors, you know, you're getting real, you've got a good resolution right at the point. The problem is they can get off calibration pretty easily as, you know, soil dries up and things change around there. The weather-based is maybe not quite as granular, down like to a tree or something like that. It's a 1 square kilometer. But yeah, we've been more maybe coming at it from the weather side of it. But we are definitely looking at more sensors as well. But they've got their own issues in terms of how accurate they are, and they can be great when you first calibrate them. A couple of months later, they could be, you know, things change with the conditions, the soil conditions, and things like that. So it's kind of an interesting problem.
In fact, that's one of, we have a patent just got awarded where we actually combine soil moisture data with this weather data to go and really see who's right? If the weather data says this and the soil moisture says that, you know, is one of them off calibration, or right, is the weather data wrong? So being able to go and figure that out is one of the areas that we're looking at right now to be able to expand. Partially, we had the idea, and now we need to convert it into implementation.
Yeah, one of the other things you were mentioning a little bit about how many devices you would need to be able to monitor it. You know, the current state of the industry, I mean, electricity, smart meters and that, they've been around for a while. They've been collecting some information. It's hard to believe how little information is being collected by on water. You know, typically, somebody's got a water meter in front of their house or in front of a business. Maybe once a month somebody goes and reads it and puts it in. They might skip a couple of months, but there's really very little tracking. It's very immature right now, and that, you know, certainly one of the things that we're getting into, and you know, one of the areas where there's definitely, you know, hardware development that can go into try to improve that. But it's a little shocking how immature the water industry is at tracking usage and monitoring what they're doing. And compared to a lot of the other industries, it's pretty far behind the curve right now. So even just having 1 meter that can tell you, like if you're in the middle of the night and nothing should be turned on, if you can see that there's water usage, you're getting information from that. And a lot of places don't even have that. You know, they're getting a reading once a month, or a lot of times they skip a month, right? You're really getting a reading once every 2 months about how much water that you just used in the past 2 months. You have no idea about, you know, whether it's reasonable or, so trying to get that kind of resolution, it's kind of an interesting problem. And it's a very immature industry right now.
Right.
It's got a long ways to go.
So it sounds like it has tremendous opportunity.
Exactly.
Dealing with real-world conditions like lightning strikes as well, circuits, that takes a lot of detailed hardware understanding.
Right.
And
Yes, sir.
another question again for our students. What does an engineer, a bachelor of engineering need to know to get a job in your company?
Brian. Brian will be hiring, so I'm gonna let him.
Yeah, I mean, we're, you know, certainly, a lot of the things we got here, digital circuit design, you know, understanding of, on the, analog design, but certainly communication theory, that's still, you know, I've been in the industry for 35 years. That course that I took in 35 years ago on communication theory has really paid well for me. And again, we're even at Hydro Point here, we're looking at.
Can I interrupt for just a moment? The students in this room that are taking 442, listen to this.
I gotta say, of all the courses that I've ever taken, that's the one that's paid the most dividends. It's just, because, you know, we're dealing with LTE now, we're gonna be dealing with 5G, there's gonna be different modulation techniques, there's gonna be different ways of, that's the one that's probably paid the most dividends for me in my career, that's
But
for sure.
a lot of the, there's also a lot of data communication, because a lot of the thing, as soon as the analog becomes data,
Yep.
you know, so that's what those of you are taking will be taking the EE 465, you need to understand this thing, because it has to do with a lot of data communications, rather than the analog communication, okay? And then also sensor, I think you said. It seems to me that our students also need to know a lot about the sensors and stuff, right?
Yeah, certainly. I mean, there's all kinds of devices being designed around that. You know, cost is always an issue. You're always going with low cost. Even though you've designed a sensor today, you know, with some new technology coming out, you may be redesigning it a couple of years down the road to try to get more cost out of it. So, yes, designs don't stay static. You know, as new technology comes out, new components come out. You know, we're constantly looking at trying to optimize that.
But I think calibration theory as well, and traceability, understanding traceability of measurements. You know, just because you've got a number, what does it relate to is a big issue.
Right.
Any other questions? Great, thank you.
Thank you.